In this video, we're going to discuss the formal definition of a limit. This may be the most abstract thing that we do in this class, so this is going to be going to take us a little time to really dissect this. So just settle in. We're also going to build our way up to performing a formal proof that a limit is a given value. So that will be in the next video. We're going to kind of build our way up. In this video, we're going to discuss what this formal definition is saying. We're going to find a delta, and we're going to find delta to make an epsilon true. So we're going to build our way up. All right, so let's start with the formal definition. Let f of x be a defined function. Let f of x be defined on an open interval about c. It's a function, obviously, except for possibly at c itself. We say that the limit of f of x approaches c is L, written limit as x approaches c of f of x equals L, if for all epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of x minus c less than delta implies the absolute value of f of x minus L is less than epsilon. So again, the real meat is in this last statement. If for all epsilon greater than 0, there exists a delta greater than 0, such that x minus c in absolute values less than delta implies f of x minus L in absolute values less than epsilon. All right, so let me draw some things out. Let's start by putting our xy scale up here, and let me just draw a curve, right? It doesn't matter what curve it is, I'm just going to draw this curve right here. What we're trying to do is we're trying to look at the limit value at this value of c. So right here, we are trying to show that this limit value is in fact equal to L. So we can see in this case the function value is equal to L, but maybe this is an undefined point, or maybe something else is going on. I don't really care what's going on at that circle. All I care about is the approach. And so we've talked about the general idea that a limit is an approach, and that is true, right? We're looking at as we come from the left, as we come from the right, we better be headed to that one spot. And that's what this formal definition is saying. It's giving us this kind of narrowing window that we better see. As that window narrows, we better get to our L value. So what I'm going to do is I'm going to set up what I call a delta neighborhood around this c. So this would be c minus delta and c plus delta. The delta neighborhood around c. And so what our definition says is that if x minus c, meaning whatever value we're at minus the c, right? So if I'm over here, this is my x value, this c plus delta, that would be my x, or if I'm in here, that would be my x. If that x minus c is less than delta, we better see that f of x minus L, whatever corresponding f of x value we're at, so this would be f of c plus delta, this would be f of c minus delta, that subtracting these two things better be less than some epsilon. And how much is that epsilon? It's just some number greater than 0. And in fact, it's all numbers greater than 0. So that epsilon does have to be any number, meaning it has to be as small as possible. So what that's kind of saying is I need to be able to squeeze that down as tight as possible, right? I need to be able to find that this x value right here, whatever we get right here, minus L, that should be able to be equal to 0.01, 0.001, 0.0000001, could be equal to 5, but it should be as big or as small as possible. And so as this shrinks, right, as this epsilon shrinks, or as that difference gets smaller and smaller, this space right in here gets smaller and smaller, there has to be an x that will get us there. So if I were to shrink this down even more, if I were to put this red line in here, there better be an x value, some c plus delta, some little amount there, some little amount of separation that will get me to that new epsilon, that can shrink as much as possible. And really the shrinking is what we care about, because we want to approach it. Obviously, if we get further away, it'd be easier. So where does that kind of break down? Let's say we had this picture. So let's claim that at c here, we had the limit value L. It's not true, it's not a limit. And the reason for that is if we were to come from the top side, right, can I find some epsilon amount away? So again, that difference from the black line, let me put that black line in there. the distance from the black line to the green line, call it epsilon. As that epsilon shrinks, is there a way for me to go back down and find some c plus delta, meaning some delta neighborhood around it that will give me that epsilon? Yes, there is, right? We can shrink that down as much as possible. However, given kind of that same amount of epsilon, we called epsilon that distance right there, going down that much, notice there's no function value. There's no way I can hit that because I have this jump discontinuity. There's never a function value in here. It's impossible for me to get back to some x value. So that's why this limit does not exist, yet this one does. So all this is saying, it's a very formal way of writing that we should be able to find a y value super close to that L, off by some epsilon, some negligible amount. Given that negligible amount, if we're off by, we should be able to get back to an x value. We should have some x value that will get us to that y value. And that's what we're saying. That's what we're looking for. So as we drive that epsilon down to 0, there has to be a delta value, some amount that we're off by that initial c. Some delta value will get us there. Let's start with this idea of finding delta. Let's start by finding delta. And let's start off really easy. So, suppose c is in the interval from a to b. And remember this e symbol looking here, this it's a stylized epsilon. This is saying c is an element of the range from a to b. If a is equal to 2, b is equal to 9, c is equal to 7, find some delta greater than 0 such that for all x where 0 is less than x minus c is less than delta, gives a is less than x is less than b. So what we're trying to do is we're pretty much just looking at one dimension right now. We're saying, hey, I know that this side over here is equal to 2, this side over here is 9, 2 and 9, those are the endpoints. And c is equal to 7, meaning we never want to be off by more than 7. What does that delta need to be? Let's think about what each of these values would be. So we would find that the c, which is 7, minus the a, which is 2, is equal to 5. This is the c minus the a. The b minus the a, sorry, the c minus the b rather, c minus the b, we would have 7 minus the 9. That would give us negative 2, but when we take its absolute value 2, these are the max amounts that we would possibly be. Now we need to choose the smaller of them, right? And the reason we're choosing the smaller is because we've got to stay inside that window. So we're saying basically, as long as I never move by more than this delta amount, I will stay in this a to b range. So I need to choose a smaller number. My delta is going to be equal to 2. That will mean that our x is always between a and b. Let's draw this out in a number line, because I think the picture really does help. What we are saying is our number line spans from 2 to 9. C is some number floating in between them. In this case, C is equal to 7. What is the max distance that I can move from any number by to stay inside that range? So as long as I'm never moving from C by more than this number, I will always stay between A and B. So from 2 to 7, there's 5 units of possible movement. So if I were to start at my 7, start at my C, and add 5 to it, subtract 5 to it, I'd get down to 2. I'd stay inside the interval, 2 to 9. But if I were to start at that 7, start at the C, and then add 5 to it, I would have gone up to 12. I would have been outside the interval. From 7 to 9, that is 2 units. If I were to start at 7, subtract 2, I'd get down to 5. I didn't hit the minimum side. I don't care. All I'm saying is I'm staying between them. I don't need to equal them. I'm just saying I'm staying between the A and the B. If I were to start at 7 and add 2, then I get up to 9. And so I'm still staying within that range. So this is essentially, this delta is giving me the wiggle room around my C to stay in my interval. The delta needs to be equal to 2. Let's take another example. This one I'm going to draw out. Again, we want to find the delta. F of x is equal to negative 3/2 x plus 3. C is equal to negative 3. The limit is equal to 7.5. We're dealing with both the x and the y direction. Epsilon is equal to 0.15. And so let's think about what we have here. I'm going to draw this one out first because the first example we were just dealing in that single variable dimension. We were just dealing with x's. Said, all right, here's an x, we want to stay between them. Now we're dealing with that second dimension. We're moving not only along the x's, but we're moving along the y's, looking at a two-dimensional picture. So if we think about the graph of this thing, it's going to look like this. It's a straight line passing through 3 with the slope of negative 3/2, meaning it's going down. We are looking in particular at a negative 3, so following that back up, that limit value should be 7.5, that's what it's telling us. And so how do we get that limit value? It's given to us in this case, but it's very easy to get because it is just a straight line. We know all the values are included. We could take the negative 3, plug it in, and that would give us the 7.5. So we are given an epsilon. Let me just clean that up, is a 0.15. What that is saying is we are never allowed to move from 7.5 by more than 0.15. So this distance right here can be 1.5, this distance right here can be 1.5, meaning we can get as high as 7.65 and as low as 7.35. That is, we are looking not really how far we're allowed to move. That is the amount we are moving right now. The 0.15 is the set amount that we're moving. We're saying, all right, is there a distance away from x, or from that c value, negative 3, that I could be? Is there a delta I can find that will keep me in those given parameters? Essentially kind of boxing in my point here, boxing in my limit. Is there a delta value that I'm allowed to move by from c so that when I find those new x's, delta units away from the negative 3, that it will keep me in between negative 3.65 and 3.35. So that's what we need to find. Alright, so I'm going to do this one of two ways. I've already actually found the y values. Based on the epsilon, I just added that and subtracted it to get this 7.65, 7.35. It's not negative, that's just a tick on my axis. So I already have those y values. So what I'm curious to see is there an x value that will give me that y value? Of course there is. It's a linear function. So let's just set the function equal to each of those two things. So I'm going to start off with a 7.65. I can subtract 3 over. 4.65 equals a negative 3/2 x. I need to get rid of the negative, and I need to get rid of the 3/2. So I'm going to multiply by the negative 2. That would be negative 9.3 equals 3x, and then I'm going to divide off the x. You could use a calculator to do this too, and you're going to get negative 3.1. Alright, so hold that number for just a second. And then I'm going to take the 7.35, the other value. I set that equal to the negative 3/2 x plus 3. I subtract the 3 over, that would be 4.35. Negative 3/2 x, multiply the negative 2 over, that would be negative 8.7 equals 3x. So my x is going to be equal to a negative. 3 goes into 8, 2, and then a remainder of 27, 2.9. So I've done these kind of out of order, not really out of order. They're fine. The negative 3.1 was the one further to the left, so the negative 2.9 is the one further to the right, but these will give me those two positions. So the question is, can I find a delta that will make sure that I don't exceed the limit value by more than those epsilons, or can I find a delta value that will get me to those epsilon pluses and minuses from the limit? And yes, I can. I just did it. So this is what we would call the delta neighborhood. The delta neighborhood are those x values that I would need to remain between in order to make sure that I don't exceed my epsilon. I don't go outside that allowed epsilon region. Not actually the delta that I wanted. The delta is how far I've strayed from the c value, which is the -3. So from -3 to -3.1, that's 0.1. From -3 to -2.9, that is also 0.1. And the way I can see that is by taking the delta neighborhood values and subtracting the c. And I get a 0.1 there. Or it really doesn't matter the order in which you subtract because you're taking the absolute value. It is the x minus c, but it really doesn't matter. When we use the 2.9, we get the exact same thing. We get a 0.1. So our delta is equal to a 0.1. Now, is it always going to be the case that the two values when we subtract are the same, like we got here, the 0.1s? No. Why was it the same? Because we had a linear function, and the rate of change is constant. Therefore, it will be the same. But that's the idea going into it. So let's be a little bit more abstract this time, because as we move into proofs, like I said, we're going to do that in the next video. As we move into proofs, we're going to have to be very abstract about these. And so I was able to actually calculate numbers here, and I was able to use those numbers to prove what I wanted. But let me switch it over, and let me use kind of the definition. Remember, what we're trying to show is that x minus delta, let me switch over to black just to, I know red sometimes we have a problem with, x minus delta, x minus c rather, less than delta implies that f of x minus L is less than epsilon. So actually what we want to do, we want to prove this, so why don't we start there? I take my function, the -3 halves x plus 3, remember that was a function, and I want to subtract off the L, which is the 7.5. I'm going to set that less than the epsilon of 0.15. We're actually, because this is what we're trying to show, we're starting with that, and we're going to work backwards to find the number that will guarantee us the result that we want. We're kind of cheating in a way, not really cheating, because we're just trying to get to what we want to show. But we're taking the answer, what we want to show, and we're using that to develop the conditions that must be met. So I'm going to start by just simplifying the inside of this absolute value. -3 halves x, that would be a minus 4.5, less than 0.15. And remember, if we have absolute values, we can drop those absolute values by creating the two-sided inequality, and we're going to have to do that. I'm going to have to set the interior of the absolute value greater than -0.15 and less than the positive 0.15. From here, I'm going to add the 4.5 to all sides, so we'd have 4.35, -3.5x, less than 4.65, and let's see if we have them yet. Those should be sounding pretty familiar, notice, right? Let's just keep working our way through. So, oops, I need to get rid of the 3 halves here. So I'm going to multiply by the 2, or let's start with just the 2, so we'd have 8.7 is less than -3 halves x, not 3 halves, just 3x now rather, just 3x, and that's going to be less than 9.3. I need to get rid of the -3, so I'm going to divide by it, but remember that's also going to switch the direction of the inequality, so we'd have a -2.9. It's greater than -3.1, and so we had to remember to switch the inequality there because we're dividing by the negative. So the only thing I did at all different from over here on the left was I just did the negative kind of in the second step. But notice we get to that same delta neighborhood. We know that the x has to be between -2.9 and -3.1. From here, we are still trying to show that the x minus the c is less than delta, or we're trying to say that we need to find that delta. That will imply all this other stuff is true. So we're still going to take the x values, the -2.9, we're going to subtract off the -3, and we're going to take the -3.1, subtract off the -3, move that over. And when we subtract each of those things, we get the 0.1s again, And so our delta is still 0.1. Again, this was just a different way of doing it. Here in black, this was just a different way of doing that problem that we did a second ago. What we did over here is we found those y values first and we just solved the equation. We're doing that a little more abstractly here. We're saying, hey, we want this to imply this thing to be true. Let's start with what we want to be true. Let's set that up. Let's kind of reverse solve that. We're just solving for x the same way we did over on the left. We're just doing so a little more efficiently inside the problem. We're getting to our delta value. Let's take one more example. This one I don't want to be linear, just so we can see how they might not have the same values when we do that x minus c step. So let's take the function g of x is equal to the square root of x minus 3. Let's take a c value of 19, the epsilon to be, we'll say 1. Let's find delta to so that the conditions hold. So x minus delta, x minus c, I keep doing that, x minus c implies, less than delta implies f of x minus L is less than epsilon. So notice in this case, I haven't given you all the L because I just want to find it. I can do that pretty easily. The limit, if it were to exist, if we let x go to 19 minus 3, we would expect the square root of 16, which is 4. That's what we expect the limit value to be. Now, we're kind of finding it, and then we're going to prove that we can stay within those regions. So the L value is 4 here. What we're saying is that the function value minus that 4, that better be less than the epsilon value of 1. So if I set up my two-sided inequality, we'd have the square root of x minus 3 minus 4 in between negative 1 and 1 once we drop those absolute values. I'm going to add the 4 to both sides, so we'd have 3 is less than x minus 3 is less than 5. Now to get rid of the square root, I have to square both sides of the equation. When I square the left, I get 9. When I square the right, I get a 25. And now to get the x all by itself, I'm going to add that 3 over, so 12 is between x is between 28. So that is our delta neighborhood around x. That is what those x values are going to span. Now what we need to figure out is what the delta should be that will keep us inside of that epsilon region. So we never leave our function by more than 1. So I'm going to take the x, start with the 12, subtract off our c, which remember was 19. When we do that, we get a negative 7, but then it becomes a positive when we take its absolute value. I'm going to take the 28, we're going to subtract 19. When we do that, we just get a 9 this time. And so we need to choose the one that is going to give us going to keep us inside that region. We can't choose the larger number because the larger number would take us outside the region. We want to stay inside that region. So for that reason, we need to choose the delta to be equal to 7. Our delta will always be the min of these two calculations. Whatever we get for those delta neighborhoods, once we subtract off our c, we're going to choose the smaller value. And it makes sense this time that they wouldn't be the same because it is a nonlinear function. It is a square root function. So that rate of change is changing. We would expect one side to be a little closer, one side to be a little bit further away. So that is how we find the deltas. From here, in the next video, we're going to do a formal proof of a limit statement.